Hey everyone, welcome back to the channel. Today we are going to be focusing on one of the core concepts of system design, and that is sharding. So we'll break down in the context of an interview what is sharding, how do you know what to shard by, how do you distribute the data, what are the main challenges that come up as a result of sharding, and how do interviewers typically like to probe into these challenges. And then we'll end really concretely with how you should address or what you should say when you bring up sharding in an actual interview. So for those of you unfamiliar, I'm Evan. I'm a former Meta staff engineer and the current co-founder of HelloInterview.com. Without further ado, let's get into it. Let's start with a simple example that's going to show why sharding exists in the first place. Basically, the motivation for why we need to shard. And so you can imagine that we just launched our app, and our app has a single, let's say, AWS RDS Postgres instance, right? So a single database, and it's a big one. It has roughly 70 terabytes of storage. It can handle about 10,000 writes per second. And in the early days of our app, everything is super smooth. Traffic grows, read volume grows, write volume grows, but everything's all good. It can be handled by what is a pretty significantly sized database here. But eventually, and maybe inevitably, we outgrow that database. And so maybe it's now that we've grown to a point where we need 20,000 writes per second, significantly larger than that 10,000 writes per second limit. Or maybe it's that our storage is approaching that 70 terabytes limit, right? In either case, the database is straining and the queries are slowing down, backups are taking forever. It's clear that we've hit some sort of a ceiling. And so what do we do now? Well, the obvious first instinct is what's called vertical scaling. And it's to say, let's just upgrade to a bigger machine, a bigger database, bigger hardware. And to be fair, this works. This works for a while. And so AWS does offer even larger machines. You can scale up to 140 terabytes of storage, something like 50,000 writes per second, depending on what your queries are. And it's worth acknowledging, this is a ton of throughput. Most companies will never ever hit this. But for the sake of argument, let's say that our app continues to grow. And so we're global now, traffic hasn't stopped, even bigger hardware isn't cutting it, and we've saturated CPU, storage, IO, everything. Our database is angry. It can no longer handle the load. And so at this point, the issue can't be solved by a bigger database. Instead, it's that no matter how big the database, we simply can't keep up. And so that's when we reach for what is called sharding. And so sharding, there you go. Sharding is the process of splitting your data across multiple machines so that no single database holds everything. And so each shard is its own standalone database, importantly. It has its own CPU, its own memory, its own storage, its own connection pool, and it stores just a subset of the data, such that together the shards form the full data set. And so we can now scale storage and read and write throughput by simply adding more shards. And if you start to grow, you add a fourth shard, a fifth shard, a sixth shard, etc. Now, importantly, sharding solved our scaling issue, that's great. But it introduced new problems, like how do we choose how to shard? How do we know which shard to route our queries to? What happens if we have a particularly hot shard? What happens if one goes down and we need to rebalance? You have to deal with all this new operational complexity that comes from having multiple database instances. And so these are the trade-offs and the strategies that we're going to explore throughout the rest of this video. How do you shard? And then how do you handle the challenges or limitations that come from sharding? The first thing that we need to decide is how do we shard our data? And that naturally breaks down into two questions. The first is what do we shard by? This is going to be the field that we use to group your data, which we call the shard key. And so for example, if you shard by user ID, that would be a column in your data, and then all data for a given user will live on the same shard. Okay. The second one here is how do we distribute those values across the shards? And so this is the strategy for mapping a shard key's values to a given machine, to a given database. And so for example, we might split user IDs into ranges like we saw in the example above, right? Where we split 0 to 10 million, 10 million to 20 million, 30 million to 40 million, etc. Or maybe we'll hash them evenly across shards, as we'll see a little bit later on when we talk about strategies. And so in simple terms, the shard key is how we group our data, and the distribution strategy is how we place those groups onto shards. Okay. And so we're going to start with the first question here, which is choosing a shard key. Let's start with that one of how do we decide what our shard key could be in the first place. And anytime you're going to talk about sharding, maybe let me actually take a step back. In a system design interview, if you're going to talk about sharding, then the first thing you should do is mention what your shard key is. Right? And you want to be explicit about this. What column are you sharding on and why? And so a good shard key has 3 properties. And we'll show examples of these in just a moment, so bear with me. But the first is what we call high cardinality. This is basically that we want a field with lots of unique values so that we can spread that data across the shards instead of piling everything onto a few shards, right? So basically the high cardinality means that we can have a good random or even distribution. And so that leads us to the second point, which is directly even distribution. And this is that those values should naturally spread out so that each shard has roughly the same amount of data, okay? And then the last one here is query alignment. Our shard key should match how we query our data. Concrete example, if most of our queries are let's get all posts for a given user, then sharding by user ID keeps all of that user data on one shard, and it means that when we want to get all of a user's posts, we only need to query one database. We don't need to go query all of the different shards, right? And so then on the flip side, a bad shard key, of course, has low cardinality. It creates uneven distribution, and it forces queries to hit many shards just to answer something simple in many cases. And so this is how you end up with all of the problems that we'll talk about in a moment, like hotspots and slow cross-shard queries. But we're going to aim for good shard keys. Let's look at examples. I got some examples down here for what could make a good shard key. And so let's first imagine in this top left one that we have a popular social media app. And the most common operation is users visiting another user's profile and loading all of their posts. This is the example we've been talking about now throughout the video. And so, as we've mentioned, in this case, sharding by user ID is a great choice because it has high cardinality. Every user has a unique ID, so we have tons of distinct values to spread across the shards. It can be evenly distributed. Users tend to arrive in fairly uniform patterns over time, so no single shard is going to end up with most of the users. And then lastly, that query alignment. Our main query is to get all posts for a given user, which maps perfectly because it means we just need to query one of these shards in order to get a user's posts, right, for the hot path. Another similar example would be that we have an e-commerce site. If we have an e-commerce site where the most popular thing that users are doing is retrieving information about a single order, both creating orders, reviewing orders, checking update statuses on orders, etc., then sharding by order ID makes a lot of sense, right? For all the same reasoning. High cardinality, it's fairly evenly distributed, and importantly, it aligns with our query pattern. But let's look at some examples of bad shard keys. Maybe this will be even more illustrative. And that's that imagine that you sharded on the value is premium, right? So in your user table, some users are premium members, some are not premium members, and that's a Boolean flag in your database. If you were to shard on this, then this gives you only 2 groups, premium users and non-premium users. And that's extremely low cardinality. You immediately cap yourself to just 2 shards, and once they fill up, you're kind of stuck, right? There's nothing else to split them on if you've chosen that as your shard key. Another bad example, which is maybe less intuitive, is in the case where you shard by creation date. Specifically, if you shard by creation date for an app in which most users are querying the most recent data. And so let's say it's our social media app again, and we've sharded by creation date of posts. So all the posts from 2023, 2024, and 2025. Well, what's going to happen here is that all of the traffic is going to go towards shard 3 here because most users are looking for the recent posts. And so we're going to end up with that hotspot on shard 3, right? So this was not evenly distributed appropriately. Now that we've talked a bit about what to shard by, let's move on to the second point here, which is how do we distribute those values across the different shards? And so there's a couple strategies. We're going to talk about 3 of them. And let's start with what is the most simple, though suboptimal option, which is called range-based sharding. And so this is the example that we've been looking at thus far because it's the most intuitive. And with range-based sharding, we take the shard key, say the user ID in this example, and we just split it into simple ranges. So shard 1 has all user IDs from 0 to 10 million. Shard 2 has all user IDs from 10 million plus 1 to 20 million, and so on, right? You get the picture. It's super intuitive. Now the problem is that this can very easily lead to uneven distribution, or at least one problem. So let's say that you have your 3 shards, your app is in its early days, there's only 1 million users right now, then only the first shard has real data and thus has real load. The other 2 are sitting there empty. Additionally, maybe more practically, is that if you were sharding by user ID, all of your new users are ending up over here, right? If you assume that user IDs are monotonically increasing, then all of your new users are ending up in these higher ranges, and all of the queries, writes and reads, are coming to shard 3, because most of the active users on your site are new users, right? Almost by definition. And so range sharding can work. It's a simple alternative, or it's a simple option, especially if your data naturally falls into these clean ranges and grows steadily. But you have to be really intentional about splitting ranges before things get too big. And you end up, or else you'll end up with that one shard taking all the heat, as I mentioned. So this is a fine option. Intuitively, it's a nice place to start, but it's not what most things use in production. And so let's move on then to what is actually used more often in production, and that is hash-based. And so let me focus your attention over here to the left before we look over at what's going on the right. But instead of using range-based sharding, the industry default is what's called hash-based sharding. Here's how it works. It's pretty simple. Instead of us just assigning ranges, what we do is we take a hash of the key, so whatever our shard key was, like the user ID, and then we mod it by the number of shards that we have. And that will tell us which shard that we should put this particular row or set of data on. The hash function basically scrambles up the input, right, randomizes it, so that we spread really evenly, perfectly evenly even, across, in our case, these 3 shards, right, the n shards. So that's a really nice big win. We get solid, even distribution, which we talked about being important earlier. But there's still some major issues with this. And the first is around rebalancing. And so if you never ever need to add or remove shards, then almost everything has to move, right? Imagine that we added a new shard here. Well, now this mod has turned into mod 4, and almost nothing, mod 4 versus mod 3, is going to land up on the same shard. So tons of data is going to have to move. Everything's going to have to be redistributed. It's a huge reshuffling of our data, which is a total nightmare operationally. Right? And so this is where consistent hashing comes in. And you've probably heard the term consistent hashing, but if not, we have a full video on it. I'm going to link it in the description. Check that out. It's pretty short. It goes over consistent hashing. But the short version is that instead of using that simple modulo, consistent hashing places both the keys and the shards on this virtual ring. And the way that it works is that you hash, you go onto the ring to wherever that hashed key lands, and then you just walk right until you find that database. And so there's some fancy techniques with this, things called virtual nodes, all of this which is in that video, which effectively eliminates that giant reshuffling problem, right? So the only thing to know in the context of sharding is that the industry standard is hash-based sharding, usually combined with consistent hashing in order to make scaling smooth. Now, in the context of an interview specifically, if you say, hey, we're going to shard and we're going to shard by user ID, your interviewer's default expectation is that you're using hash-based sharding with consistent hashing. In many cases, you don't even have to say it, especially if you're senior plus. That's the expectation. There's no reason to even bring it up. If you are more junior, mid-level, they might ask you, how is this sharding happening? In which case, you can inform them about how hash-based sharding and consistent hashing actually works. Let's look at the last one here now, and this is something called directory-based sharding. And so instead of using a formula to decide where data lives, directory sharding uses a lookup table. And so for each record, say each user, you store which shard they belong to in this lookup table. And so you simply, on each read or write, have to first come here, find out which shard they belong to, and then go to the right shard specifically. And so the big advantage here is flexibility. If one user suddenly becomes super popular and starts generating a ton of traffic, you can move them onto their own shard easily by just updating this mapping. If shards start to get overloaded, you can redistribute with this mapping. You can basically implement all of this custom sharding logic by being explicit about which users or which shard key matches to each shard, respectively. But the downside is pretty obvious, and you guys might be thinking this as you're hearing me talk through this, and that's that every single request now has extra latency. It needs to first look up here into the directory and then actually query the shard as opposed to just one query to the shard. And so that's 2 requests now for every single lookup, which is going to add a bunch of extra latency. And it also, maybe even more importantly, is going to create a single point of failure, where if this directory goes down, well, then we're pretty screwed until we pull this back up because we have no idea where all of our data exists on each of these shards, right? So directory-based sharding has its place. It's great when you absolutely need that maximum flexibility and you can afford this extra hop, but very important, in a system design interview, it's almost never the right answer. And so this introduces that single point of failure, it adds the extra latency from the 2 hops, and it's just going to invite a bunch of follow-up questions that might derail your whole interview, right? So my suggestion to you is in practice, especially in interviews, just default to your hash-based sharding with consistent hashing. Know that the others exist in case you need them, particularly in order to get out of some of the challenges, which we'll talk about in a moment. But this one's your default. It's your bread and butter, and it's the one that you should know best. Really quick, before we continue, let me tell you a little bit about the most popular feature on HelloInterview.com, Guided Practice. It's an interactive tool that lets you practice system design interviews step by step using that Hello Interview delivery framework. You're going to walk through everything from the non-functional requirements to the core entities, API routes, all the way through to your high-level design and deep dives, drawing on the whiteboard and narrating your response, all while getting real-time feedback on what you're doing well and where you can improve by a model that Stefan and I have spent hundreds of hours tuning. We've expanded the library to 25 of the most common system design interview questions now, and we're constantly adding more. So candidates absolutely love this feature. I think you will too. Check it out at hellointerview.com. Link will be in the description. All right, now that we know all about how to shard, let's talk about the challenges that come along with sharding. Because frankly, these are the follow-up interview questions that your interviewers are going to throw at you and that you obviously want to be ready for. And so the first and the most common problem is around hotspots or load imbalance. So let's look at that one first. Even with a good shard key, some shards can end up taking on way more traffic than others. Let's give the classic example of what's called the celebrity problem. And so let's say we sharded by user ID, and Messi happens to land on shard 1. Of course, Lionel Messi, the famous soccer player. And so anytime someone views his profile or comments on his posts or likes something of his or sends him a message, all of that traffic is going to shard 1. Now suddenly shard 1 is orders of magnitude larger in its write throughput than the other shards, right? Because Messi is there. And so most other ones sit there cold, where this one got really, really hot. And so what do? Well, the first solution is what's called a compound shard key. You guys have seen me use this in other videos. And it's instead of sharding purely based on user ID, you add some additional suffix or some piece of data before hashing. So whereas before, it might have looked like this, right, in order to get that key. Now it can be user ID plus n, where maybe n is a number of the number of shards that you want to distribute this over. Or if you want to further distribute by time, you could do something like this, right? You can add another column here. But the point being is that by adding something else to the input of the hash function, we're going to further distribute, in this case, Messi's posts across multiple shards, right? And then the second solution that we can do is that you can have, and this one's fairly popular as well, a dedicated celebrity shard. And so this is where you can detect the high traffic users and move them into their own specific shard. And so maybe you end up with a shard 4 here. This is the celebrity shard. Maybe it's even bigger, like it has special hardware. And now we use that directory-based lookup to say, hey, if you're a celebrity, now the thing's a little big, but you guys get my point, right? Let's first look here. If you're a celebrity, well, then I'm going to route you to the celebrity shard. Otherwise, we're going to do the hash base with consistent hashing, and you're going to go to your normal shard, right? And so most systems won't end up needing this, but if your platform has extreme outliers, like a social media app does, in this case with Messi, then it's a really powerful tool, right? You either want to append here with compound shard keys or have a dedicated shard for celebrities. Now, the next most common issue that you run into is something called cross-shard operations. And so this happens when your data lives on multiple machines, so that any query that needs information from more than one shard suddenly becomes expensive. Because instead of hitting a single shard, you need to wait, or you need to fan out and query, in some cases, many or even all of the shards, and then wait and aggregate them and return that back to the user, right? And so this usually happens when your query doesn't align with your shard key, which we talked about earlier. And so if we were to shard users by user ID in the example we keep giving, then a request like get user 123's profile is super easy. That's going to hit one shard, it's going to be fast, and it's going to be quick. But if the query was like, give me the top 10 most popular posts across the whole platform, well, now we have to go get the most popular parts from posts from each shard, bring them into memory, right? Aggregate all 30 of those, rank them, and then return the top 10. And you can see how obviously that's much more expensive. And now the reality is that you can't eliminate cross-shard queries completely. It's unfeasible. But The first line of defense is, of course, choosing a good shard key that aligns with your most common queries so that you don't have them happen that often. But even with a perfect shard key, you'll still have these global queries when you have something like top posts in the example that we've shown here. So what can you do? Well, the first and maybe most common solution is that you can cache the results of these expensive cross-shard queries. So if I had some cache here, maybe something like Redis, then yes, the first time a user asks for the most popular 10 posts, it's going to be expensive. We're going to do that scatter gather. We're going to query all of the different shards. We're going to aggregate. But then we're just going to cache it. And so the next time they ask, we're going to be able to just hit the cache. Right? So you get one expensive one, and then everything else hits the cache. Maybe we put an expiration on this for just like 5 minutes. And this, of course, has us playing with that compromise, where we are trading latency for consistency or the staleness of our data. Because now what's going to happen is that users who query us in 4 minutes later are actually going to get the top 10 posts from 4 minutes ago, not from right now. But in most cases, feeds, leaderboards, trending pages, etc., that's a worthwhile trade-off. And so it's one that we make. Another option is that you can denormalize your data so that related information lives together. And so denormalization, of course, is the process of repeating data such that you're making your queries quicker at the expense of multiple writes. And so let's say there is some query for which you need to go to shard 1 and shard 2, but it's something that you're doing a lot. And so what you could do is you could take the data from shard 2 and also put it alongside that table in shard 1 where you're constantly making this query. Now you only need to hit shard 1 and you get the data, but that data lives on both shard 1 and shard 2. So now on writes, you have to write it in 2 places. And so this is another trade-off, of course, right? Now you are trading making writes more complex, but making reads stay within a single shard. And so, classic scaling trade-off. Pay a little extra on writes, but make reads faster and cheaper. It all depends on your design and your requirements, whether or not this is right. But the main takeaway for you in an interview is if you find yourself constantly querying across all shards for a common use case, that's a signal that either most importantly, you chose the wrong shard key. So wrong shard key. 2, that you should cache or pre-compute, like we showed in that example. Or 3, you should denormalize your data in order to keep it together. Right? So cross-shard queries should be the exception. They shouldn't be the norm. And then last up, in terms of the main problems that come up, is consistency. And so when all data lives on a single database, then database transactions, they're super easy. Let's kind of root this in an example, the classic banking example. You have Bob, who has a banking account with $10, and Alice, who has a banking account with $10. And Bob wants to send $5 to Alice, right? Well, in a traditional relational database, this is one atomic transaction. And you can see it here. This is what the database transaction would look like. We remove $5 from Bob, we add $5 to Alice. And the atomic nature of this transaction makes sure that both of these commands succeed or neither of them succeed, right? So we never end up in an inconsistent state. But once Bob and Alice live on different shards, as is the case here, shard 1 versus shard 3, then things start to get messy. And not the same messy as earlier, right? They start to get messy in the bad way. And that's because now these updates can't happen in one atomic operation. And so what happens if we do this deduction of Bob, but then this increase to Alice fails, or even the other way around, right? We end up in that inconsistent state, which is bad. And so the textbook solution, which you've probably heard a handful of times, is something called two-phased commit, oftentimes denoted as 2PC, like that. And basically, there's a central coordinator, and that central coordinator first asks all shards, hey, are you guys ready to do this transaction? And then it waits for everyone to say yes before telling them all, okay, now it's time that you can commit. And this ensures the consistency. And it sounds great in theory. In practice, two-phase commit is actually pretty slow and fragile, because if any shard or coordinator goes down in the middle of it, then the whole thing can get stuck, and you end up in this lock, which is super tough to get out of. And that's why most production systems actually try to avoid 2PC to some extent. And so what can you do instead? Well, option 1, for fear of being annoying here, would be, well, try to avoid cross-shard transactions, right? In your system design interview, to the extent that you can, if you have a transaction, try to make sure that all that data is on the single database. That should be your golden rule to try to follow. Now, it's not always achievable, as is evidenced with our example here. Alice and Bob exist on different shards, and there's no way that we could guarantee that the two people who are involved in our bank transaction exist on the same shard, right? And so another option is something called the saga pattern, another thing you might have heard the buzz term for. And so this works basically using a sequence of smaller operations. Each action has what's called a compensating action that can be run in case things fail. And so I'm not going to get into too much detail here. I'm going to leave going deep in saga patterns. We actually have a scaling rights write-up, which I'll put in the description that you can read more of. But the basics is this. Step 1, deduct 5 from Bob on shard 2, or on shard 3, excuse me. Step 2, add $5 to Alice on shard 1. And then if step 2 fails, we don't magically roll everything back. Instead, we run what is that compensating action for step 2, which I had mentioned, which is that we're going to refund Bob his $5. And so it's manual, but it ensures that we don't end up in a broken state because it says each action we take has an opposite compensating reaction such that if anything fails, we'll run that compensating action in order to get back to the state that we want it to be in. So a little hard to describe in brief, but look up saga pattern on your own or read that scaling rates breakdown because I don't want to go into too much detail here. But the mental model that you should be thinking of here when it comes to maintaining consistency is basically first, try to avoid cross-shard transactions in the first place. If you do have them, the saga pattern is really useful. It's such that instead of one big transaction, you chain smaller steps together, each of which have a corresponding undo action associated with them. All right, lastly, before we sign off, and maybe the most important thing is let's talk about how sharding comes up in system design interviews. And so you're going to bring up sharding in your interview during your deep dives, typically towards the end of the interview, when you're satisfying a non-functional requirement about scaling. So as you're thinking about scaling, you're going to head over to your database and you're going to think, from the perspective of both storage, write throughput, and in some cases read throughput, do I reach any of the capacity limits and can I justify that I do? If yes, I need to determine that I can shard. And so let me show you what that looks like, right? Specifically starting with storage. I could say something like, well, we have 500 million users with 5 kilobytes of data each, and so that's 2.5 terabytes of data. A single Postgres instance is going to handle that, so we don't need to shard. But if we ended up growing 10 or 100x, then we would shard, okay? Write throughput, we're expecting about 50,000 writes per second during peak. A single database would struggle with this write load, so we should probably shard. Read throughput similarly, even with read replicas, if we were serving 100 million daily active users, making multiple queries each, we'll need to distribute this real load across shards, probably do some math about how many read queries that would end up being, and prove that it exceeds any thresholds. Now I put this in red because this is important. And you saw this with the first example. You don't always need to shard. In many of the system design interviews that I'm in, it's the reflexive nature of most candidates that say, oh, I need to shard and I'm going to shard by this. But that's wrong. Like modern hardware goes a really far way. You saw in our intro example, you had a Postgres database with 140 terabytes of storage. That's a ton, right? 50,000 writes per second. And so it's sometimes the case in these interviews where it actually can be really impressive to show your interview, actually based on this math, I don't need to shard. Right? 500 million users, 5 kilobytes of data, that's only 2.5 terabytes of data. And we're going to have limited throughput, so no need to shard. But in the case where you do prove that sharding is necessary, then what do you say? Well, you follow these really simple 4 steps. The first thing that you're going to do is you're going to propose a shard key based on your access pattern. And so, for example, for this social media app, most queries are user-centric. When someone loads their feeds, we're querying for all of their posts, their followers, and their likes, and that's all scoped to a single user. So I'm going to shard by user ID. Easy. The second one, you're going to choose your distribution strategy, right? And so this is where you could say I'd use hash-based sharding with consistent hashing to hash the user ID to distribute users evenly across the shards. Now, as I mentioned earlier, you might be able to skip 2. This is kind of the default. This is what your interviewer is expecting you mean when you say you're going to shard by user ID. But for the more junior roles, junior and mid-level, it might be worth saying. The third thing that you're going to do is you're going to call out those trade-offs. And so you might say the trade-off is that global queries are going to become more expensive. If we need trending posts across all users, then we'll have to query all the shards and aggregate the results. But we could handle this by caching trending content, pre-computing it with a background job, etc. And this is where you'll talk about those trade-offs we discussed. And then the fourth is you want to address how you'll handle that growth. And so, we're going to start with 10 shards, which gives us room for significant growth, but consistent hashing is going to make it easier for us to add shards later and reshard the data if we need to, and we end up needing more capacity. Right? So that's the 4 steps that you want to do. This conversation should be simple, it should flow naturally, and most importantly, it should be justified based on the numbers that you calculate, either on storage, write, or read throughput. Awesome. Okay, I hope that this was useful to you all. I know that this was just a quick hit on sharding. We have the written write-up that I suggest you go read. It has a little bit more detail, but this is a foundational core concept to system design that you should know for your interviews. Go ahead and leave some questions, comments, anything I got wrong. I'll be in the comments responding to them. Check out the website, hellointerview.com. Lots more content just like this. Check out the YouTube channel, plenty more videos, and more on the way. So thank you all for watching. Best of luck with the upcoming interviews, and I'll see you all soon. Bye-bye.